So this is joint work with my advisor, Alex Aiken at Stanford. Binary translation, as I use the term in this talk, is the ability to run software written for one instruction set architecture or ISA on hardware that implements another ISA. There are many applications of binary translation, the most important perhaps being portability, which is the ability to run legacy applications on current hardware. One popular example of this is Apple, which moved its PowerPC applications to its new Intel line of chips recently, and they use a binary translator called Rosetta to do this. Another application is virtualization. Almost all virtualization engines have a binary translator today. Although virtualization does not necessarily mean running one ISA on another, it does mean running system-level instructions on emulating them at user level. Binary translation is useful for backward and forward compatibility of architecture generations, such as Intel. It has been used in the past by Transmeta Crusoe in hardware to reduce power consumption on chip. And in software, it has been used to improve efficiency of virtual machines like Java. So in summary, the slide is saying that binary translation is an important technique. A binary translator could be present at different layers of the software stack. For a virtualization engine, it will be present in the hypervisor, translating the guest operating system as it's running. For a scheme like Apple Rosetta, it will be a part of the operating system, translating the application as it's running, in this case, a PowerPC application to run on x86. Or a binary translator could be itself a user-level application, which is translating another user-level application as it runs. The four main difficulties in constructing a binary translator. I list four of them here. The most important perhaps being performance. Almost all binary translators incur an overhead and hence a loss in performance. And in building a good binary translator, you need to make sure that this performance loss is minimal. It is also difficult to kind of write a good optimization engine to support large and complex instruction set architectures, and Intel x86 falls in that category. Retargetability is an important desirable for a binary translator. Most good performing binary translators today are very tightly coupled to the source and the destination architectures that are supporting, and it'll be nice to have. So retargetability is an important desirable. And finally, if your binary translator is a user-level translator, you need to ensure compatibility between the OS interfaces on your source platform and in your destination platform. In this talk, I will talk about a technique that alleviates the pain involved in the first three issues that I list here. The technique that I'll talk about in this talk is called Peephole Superoptimization. Here's an outline of my talk. I'll first define superoptimization and what it means. And I'll talk about the technique of Peephole Superoptimization. And then I'll talk about how we apply this technique to binary translation. Finally, I'll talk about our implementation, experimental results before concluding. So superoptimization. Superoptimization is a term that was coined by Henry Massillon in 1987 to describe a unique kind of code generator that uses brute force search to attempt to find the optimal code for a given target function. He used the term superoptimization or superoptimizer to distinguish it from a garden variety optimizer, which are usually interested in improving code and not necessarily producing the optimal code. And this system, on the other hand, is trying to do that by using a brute force search mechanism. For example, an example from his paper is shown on the slide, where on Motorola, he shows that the signum function can be computed in 4 instructions, which is a little non-intuitive and surprising at first, without any branch instructions. So how does a superoptimizer work? It's a very simple idea. You enumerate all sequences up to a certain length, and you compare each enumerated sequence with the target function for equivalence. Henry Massillon, in his original paper, was able to scale up to 12 instructions, instruction length sequence. However, the size of the enumerated sequence really depends on the size of the instruction set that you constrain your system to. If you were to support a full, all the instructions in a typical architecture, you typically scale to around 3 or 4 instructions using this technique. So what is Peephole Superoptimization? A Peephole Superoptimizer is a system that uses a superoptimizer to automatically infer Peephole optimizations. Peephole optimizations, as lots of you may know, is basically a pattern matching rule which says that if you see a pattern of the form X, then it's safe to replace it by another pattern Y, which is perhaps faster or better in some way. So here in this slide, I show some examples of Peephole optimization. The first one says, if you see an instruction which says add 1 to a register, it's safe to replace it by an increment of that register. So I'll describe how a Peephole superoptimizer works at a very high level in the next 3 slides. The system works in 3 steps. In the first step, you take a set of representative executables and scan them for instruction sequences to harvest sequences that can potentially be optimized. These instruction sequences are canonicalized, or in other words, the duplicates from these instruction sequences are removed up to register renames, and they're stored as a table of target sequences, which I show on your right. This table of target sequences are the sequences which we are interested in optimizing. In the next step, a brute force optimizer or superoptimizer is used to search through the space of instruction sequences to find an optimized version of one of the target sequences. The brute force optimizer basically enumerates all instruction sequences exhaustively in a brute force manner and checks each of them for equivalence with one of the target sequences. Because you need to enumerate and compare for equivalence billions of instruction sequences, you need a very fast equivalence check. So for the equivalence test, which is basically a module that takes in 2 instruction sequences and returns an output whether they're equivalent or not, is split into 2 steps. The first step is the execution test, which is a very fast test and can complete in microseconds. And the second test is a Boolean satisfiability test, which is a slower test. The first test basically executes the 2 sequences on random inputs to see if they result in identical outputs. If the 2 sequences pass the execution test, then the Boolean test basically uses a satisfiability solver to determine equivalence. So most of the sequences, however, fail the execution test, and hence we can really cycle through a lot of instructions very fast. And finally, once we have computed the optimized sequences for the target sequences, we combine the 2 tables to form a table of pattern matching rules, which says that if you see a pattern similar to that of the target sequence, it is safe to replace it by a pattern of the optimized sequence. This table of Peephole optimizations, once learned, can be then applied repeatedly to perform optimizations. So we wanted to use this technique to perform code generation in general, and binary translation looked like a compelling application that was also a good fit to this approach. Our approach to binary translation is to use lots of Peephole transformations to translate code from one architecture to another. So for example, if we wanted to translate code from PowerPC to x86, could we say something like, if you see instruction add I R1 R1 1 on PowerPC, please replace it by increment of EAX on x86. But that does not make sense, because how do we know that R1 on PowerPC corresponds to EAX on x86? And so we need another column which specifies this mapping, which we call the register map. So now this rule says that if the register R1 on PowerPC is mapped to register EAX on x86, then you can replace add I R1 R1 1 with increment of EAX. So here are some examples of Peephole translation rules from PowerPC to x86. The middle column is the register map. Notice that while I call it a register map, it is not really a map only from registers from the source architecture to the destination architecture. In fact, if you were to translate code from PowerPC to x86, the source architecture has 32 registers and the destination architecture has 8 registers, and so we have to spill some registers to memory. Hence, it's a map from memory and registers on the source to memory locations and registers on the destination. The second Peephole rule in this table, for example, shows a rule for where register R1, PowerPC register R1 is mapped to memory location MR1 on x86. This register map column is the main difference between a Peephole optimizer, and a binary translator as we construct it. It is important to choose the right register map, or choose the register map wisely to have a good quality of translation. We call this the problem of register map selection, and I'll make two observations about this problem. The code that you're translating may use different registers more frequently than the others at different points in time, and hence the register map may need to change at different code points in the executable. And secondly, the choice of the register maps directly affects the choice of the instructions that you choose to translate, and the instructions you choose directly affect the register maps you use at the successor code points. And hence, these problems are correlated. To motivate this problem and our solution, let us consider a simple PowerPC sequence that we want to translate to x86. Here's a sequence of 4 instructions that uses 2 registers. It's doing nothing special. And we want to translate it to x86. Let us assume a simple cost model where each instruction is given a cost of 1 unless it accesses memory, in which case it's given a cost of 10. Also, if you were to change register maps from one code point to another, it will involve swapping in registers from and to memory, and hence this cost of switching register maps is captured in switching cost. And let us assume that the cost of switching a PowerPC register from register R on x86 to memory location M is 10, and vice versa, is also 10. And also, let's also assume that in the simplified example, we are given that at entry, both R1 and R2 are stored in memory locations, and so is true at the exit. So the question is what register maps to use at points P0, P1, P2, and P3, and hence what instructions to correspond to generate for the x86 code. So I'll go over a strategy to show what does not work, and this is the greedy strategy. The greedy strategy basically tries to optimize the cost at that particular point without worrying about what happens in the future. And if we were to use the greedy strategy, the first instruction, which loads an immediate value of 1 to 3 into register R1, gets translated into a move to a store to a memory. So basically, the red arrow on the slide shows the switching cost, which is 0 in this case because register R1 stays in memory. And the blue cost that I show at the end of the row is the cost of the instruction, which is 10 because the instruction is accessing memory. Similarly, this next instruction is, in the greedy strategy, is going to be treated similarly, and R2 is going to be kept in memory, and you're going to emit an instruction accessing memory. The third instruction does a similar thing. And so basically, we end up with a code fragment that looks at like that on the right. This code segment does not involve the switching instructions, which would be loads and stores to kind of get PowerPC registers from and to memory. But what I'd like you to notice about this code fragment is that almost all instructions are accessing memory. And the grand total cost of using this greedy strategy is 60 in this particular simple example. If you will look at this optimal solution, it turns out that the better way to do it is just kind of load the PowerPC registers first into x86 registers and then perform the 4 instructions on the 2 register-loaded values. This results in a much cheaper cost of 44 in this particular example. So we use dynamic programming to attempt to achieve the optimal solution. We cannot always do that because it sometimes gets we sometimes need to prune the search space. In our dynamic programming formulation, we account for translations that involve multiple instructions from the source to the destination architecture. And this approach allows us to simultaneously perform instruction selection and register mapping. So this is the approach we use to binary translation in our implementation from a PowerPC to x86. Other approaches have been used, and the most popular approach to binary translation has been the idea that you first decompile the source architecture instructions, binary instructions, into a higher-level intermediate language, and then recompile them into the destination binary format. The difficulty in that approach is the design of that intermediate language and then the writing of that optimization loop for that language. And that is the approach that's been used by the software behind Apple's Rosetta. And I will be comparing our approach to that. So in our implementation, we have developed a static user-level translator, which is capable of translating a 32-bit PowerPC Linux binary to a 32-bit x86 Linux binary. We have been able to we have translated most, but not all system calls, and hence our translator implementation is not yet complete. But we have been able to translate many benchmarks using our translator implementation. For our Superoptimizer, we use a PowerPC emulator called Chemu for our execution test. And for our Boolean satisfiability test, we use a satisfiability solver called ZSHAF. There are many implementation issues that are discussed in the paper. And in the interest of time, I won't go over them, except discuss two of them. Endianness. So PowerPC is a big endian machine, while x86 is a little endian machine, and so we need to account for that. We deal with that by making sure that the memory stays always as a big endian in the big endian layout, while registers are maintained in little endian. So we convert all memory writes to big endian before storing them to memory, and we convert all memory reads to little endian before storing them in registers. Another interesting observation we made during our experiments was compiler optimizations. PowerPC optimizers typically stagger data-dependent instructions far apart to minimize pipeline stalls. This does not play well with our Peephole translator because we would like data-dependent instructions to be as close together as possible. To deal with this, at a basic block level, we rearrange instructions so that data-dependent instructions are kept as close as possible before feeding them to the translator. So here is the setup of our experiments. We use a Pentium 4 to do our experiments, and we use a particular version of GCC to compile our executables, both for PowerPC and x86. Our translator is currently not capable of handling floating point instructions, and so we use a softfloat library to compile our benchmarks. And because our translator is a static translator, we use statically linked input executables. In our benchmarks, I'll use a few compute-intensive benchmarks, micro-benchmarks, basically to try and understand the characteristics of the system and to stress test it, and the Spec integer benchmarks. In making the comparisons, I compare against natively compiled code, and I'll compare against other binary translators that are Chemu and Apple Rosetta. For our experiments, there are around 750 translation rules in the Peephole table. It can take up to a week to compute this Peephole table, but once the table is computed, it can be used repeatedly to translate executables. In our experimental setup, we start with C source of the benchmark and compile it using GCC for the two different architectures on the two branches. Exactly the same optimization options are used for both branches. So for example, if you use O0 on the left, you will use O0 on the right, and O2 on the left means O2 on the right. Then the PowerPC executable is translated using our translator. And finally, the translated executable's performance is compared against the natively compiled executable. Okay, I'll start with a few micro benchmarks that we just picked to understand the system behavior and stress test our system. The first benchmark is an empty loop, which is basically tight loop that counts up to a high number doing nothing. Fibo is a benchmark that computes the first few Fibonacci numbers. The three well-known sorting algorithms. Three different algorithms to compute the towers of Hanoi problem. Traverse is a linked list repeatedly. And binary search, bin search is basically a binary search on a sorted array. So here's a chart showing the performance of our translator relative to a natively compiled executable on these micro benchmarks. The y-axis shows performance relative to the natively compiled executable, and higher bars are better. 100% means that the performance of the natively compiled executable is equal to the performance of the translated executable. I show three different bars here for the three different optimization options used on both branches, O0, O2, and O2 with omit frame pointer. And I'll discuss why I needed the third one. the median performance on these micro benchmarks is around 90%. And the surprising thing when we did this experiments was that in 3 of these micro benchmarks, we were getting performance above 100%. And in one of these, actually, we were getting 3 times the performance of the natively compiled executable, so it was very surprising. And when we looked into it, we found out that because GCC uses one dedicated register to store the frame pointer, our translator has an unfair advantage, and hence we use the third bar to make a more fair comparison. But still, why are we doing better than the natively compiled executable on 3 of our benchmarks? Well, we found out that we made 2 observations. We found out that GCC generates sometimes better code for PowerPC, perhaps because it has the luxury of many registers on a RISC architecture. And our register mapping algorithm, our dynamic programming-based register mapping algorithm, is doing a good job at register reallocation. So basically, our register mapping algorithm is basically doing a register reallocation from the 32 registers to the 8 registers on the CISC architecture. Okay. So next, this chart shows the performance of our translator on the Spec integer benchmarks. We were able to translate 7 of the 12 benchmarks. The others failed because of either bugs in our translator or due to the incomplete support for all system calls yet. And in this chart, you'll find there's a missing bar for Vortex, which again failed for O2. The median performance on these benchmarks is 67% of the natively compiled executable. And one of the surprising results is the performance of 12, which is significantly higher than that of the natively compiled executable. This is actually because of a weird behavior in the glibc soft float library, which incurs extra overhead in the x86 code, and also good translation by our translator. All the other benchmarks spend almost 0 time in the floating point library, so we don't see this effect there. Next, I'll make comparisons with the other available binary translators, Kemu and Rosetta. For Kemu, we use exactly the same executables that we use for our translator to perform comparisons. And for Rosetta, we were not able to do that because Rosetta translates macOS executables while our translator is written for Linux. And hence, we recompiled the benchmarks using exactly the same compiler version to minimize any bias to make comparisons. I'll point out here that Kemu and Rosetta are both dynamic binary translators, while our translator is a static translator, so their results includes the overhead of doing the translation itself, while our translator does not. And in the next slide, I'll discuss what that overhead is for our translator. So this chart shows the comparison with Kemu and Rosetta for O0 and O2 executables. For Rosetta, we were unable to get numbers for 2 of the benchmarks, GAP and 12. For 12, Rosetta hung on the PowerPC compilation, which indicates perhaps a bug in their translator. And for GAP, we were unable to get a compiled version for macOS. In general, we are 1.3 times to 4 times better than Kemu. And we are 3% faster on Rosetta and on O0 executables, and 12% faster than Rosetta on O2 executables. So what is the translation time of our translator? Well, our static translator takes around 2 to 6 minutes to translate an executable, which is a typical Spec benchmark with all the statically linked libraries pulled in. This seems unacceptable in a dynamic translation environment. However, I mean, when you are doing a dynamic translator, you do not need to translate the entire executable. In fact, 98% of the executable was almost never executed, and hence, if a back-of-the-envelope calculation says that we expect the translator overhead to be less than 10 seconds, or roughly 4% for the Spec benchmarks. Well, while it's not possible to quantify this exactly without building a dynamic translator, this calculation shows that there is, we should be fine. So in conclusion, this is a scheme to perform efficient binary translation, which has a simple design and performance which is competitive to existing commercial binary translator tools. And we want to, in future work, understand how we can use this approach to solve the problem of code generation in general, for example, just-in-time compilation for Java, and look at other applications in the field of machine virtualization. Thank you.
Lin Tan from Illinois. So it seems you need to match 750 patterns on each run. So I wonder what pattern matching algorithm you use, and if you use a faster pattern matching algorithm, would that give you much more performance benefits?
Yeah, I mean, our pattern matching algorithm is very simple, and we have tried to optimize it as much as possible. But if there can be any improvement there, it should show up in the translation time overhead. Yes.
Hi, Bo from Fudan University. I wondered if the Superoptimizer is thread safe. If it's not, what's the potential effort of doing so?
Is it thread safe?
Thread safe.
Thread safe?
Yeah.
Okay, the question is the Superoptimizer thread safe? Well, Superoptimizer is a code generator. So, I mean, I don't understand what it means to be a thread safe or not, but is our binary translator thread safe? Is an interesting question. And our prototype implementation we have designed it in such a way that it should be thread safe, but we have not yet tested it on multi-threaded applications, so it'll be hard to say. So is that an answer question? Yeah.
Hi, I'm Eric Ide from the University of Utah. I had essentially the same question, so I'll just follow up. So one of the issues in translating a concurrent program, right, is proper handling of the synchronization between the threads in the source program to the target environment, right? So, for instance, it might be incorrect to translate a memory location into a register on the target platform because the write to the memory is important for the synchronization. You see what I'm saying?
That's a valid point, and yeah, we have not thought about it yet. In our prototype implementation, because we're doing PowerPC to x86, we have never had to pull memory locations into registers. In fact, it's been always registers spilling to memory. So we have not run into this issue, but that's an interesting point, and any binary translator needs to take care of that. Our focus on this work has been really on code generation and kind of optimizing the code generation part of the binary translator.
Thank you.
Thank you.
Bernard Wong, Cornell. It seems with the number of problems associated with static translators that having some type of dynamic translator support would be useful. And I was wondering how much of your optimization techniques would translate over to a dynamic translator.
So, yes, I mean, the reason we went for a static translator was basically because of its simplicity and clean separation between translation time and runtime to understand while we are developing it. Yes, I agree with you that a dynamic translator is the only practical solution, really, and a static translator is more of a prototype solution. How much of our optimizations are going to carry over to dynamic translation? I don't see any reason why the same performance is not going to be is not possible in a dynamic translator, because we are basically doing a pattern matching translation from the source to the destination. So I don't expect any performance loss due to that, but there will be a overhead of translation.
Krista Wilson, UCSB. So in the paper, you mentioned that you can handle instruction equivalence even in the face of aliasing, which is a traditional problem for static analyzers. Can you go into that a little bit more?
So yes. So our execution test is clearly susceptible to aliasing problems, but our Boolean test is capable of handling aliasing. We have built a memory model in the Boolean logic to kind of make sure that aliasing problems can be resolved properly. More details are in our actually previous paper on Peephole superoptimization in our AS+ paper. Yes. Thank you.
Excellent job on the timing.